All right, let's get right into it. We're going to break down the physics behind something we've all done. Just, pushing something across a room.
You totally know that feeling, right? You get down, you plant your feet, you lean in with all your might. What is actually happening in that moment of effort? Well, it turns out it's a really fascinating story all about energy. And to tell that story, let's introduce our main character, this box. Right now, it's just sitting there, not moving at all. In the world of physics, that means its energy of motion is a big, flat zero. And our whole goal is to change that. See, when you move something, you're not just changing where it is. You are fundamentally changing its energy.
This energy of motion has a special name. It's called kinetic energy. So, an object that's standing still, zero kinetic energy. An object that's moving, it's got some. Our mission, should we choose to accept it, is to give this box some kinetic energy.
So how do we do that? We can't just stare at the box and hope it starts moving. We have to do something, an action that physicists call work. Now, hang on. When a physicist talks about work, they don't mean your 9-to-5 job. Work is the actual physical transfer of energy. So when you apply a force, that's your push, and the box moves a certain distance, you are officially doing work. You're literally transferring energy from your body into that box. And here is, I think, the best way to picture this. Imagine the box has a kinetic energy bank account. Right now, the balance is 0. When you do work on it, you're trying to make a deposit. The currency we use in this energy account is called the joule. That's the standard unit for energy and work. But what even is a joule? Like, what does 1 joule actually feel like in the real world?
It's actually a lot more tangible than you might think. If you grab a small apple, which weighs about 100 grams, and you lift it up by 1 meter, so about 3 feet, the work you just did is about 1 joule. It's a real physical thing. Okay, so let's go back to our box, because this whole bank account analogy is about to get really, really useful. Your push isn't the only force acting on this box. And it turns out not every force makes a deposit. This is where things get interesting. What about all the other forces at play? I mean, what about friction? That scraping feeling between the box and the floor. Is that helping you out? Is that another deposit? Well, your push is in the same direction as the motion, so that's what we call positive work. That's your deposit into the account. But friction always opposes motion. It's fighting against you. So it does negative work. It's like a withdrawal, actively taking energy out of the account. Okay, but what about the other big ones? We've got gravity pulling the box down, and we've got the floor pushing right back up to hold it. Are those deposits or withdrawals? The answer, surprisingly, is neither. Because those forces are acting up and down, perpendicular to the direction the box is sliding, they do 0 work. They can't make the box go faster or slower horizontally. So, in our bank account analogy, they're like bystanders who just watch the transaction happen. They don't touch the money. So this brings us to the grand finale. To figure out what actually happens to the box, if it speeds up, slows down, or what, we need to look at the final transaction summary. We have to add up all the deposits and all the withdrawals. Let's throw some numbers in here to make it real. Let's say you push that box and your effort results in a deposit of positive 650 joules of work. At the very same time, that pesky friction is fighting you every step of the way. It does negative 590 joules of work. That's a 590 joule withdrawal from the account. So what really matters is the net transaction. We take your plus 650 joule deposit and we subtract the 590 joule withdrawal from friction. The final result, the profit, if you will, is a positive 62 joules. And this leads us to a really beautiful and fundamental rule in physics. It's called the work kinetic energy theorem, and all it says is that the net work you calculate is exactly equal to the change in the object's kinetic energy. It's a 1-to-1 relationship. So that profit of 62 joules, that's what actually gets added to the box's kinetic energy account. That's the energy that makes the box accelerate and speed up. Your push was just a little bit stronger than friction, and 62 joules is the payoff. But, there's one more piece to this whole story. Because in the real world, it's not just about how much work you do. It's also about how fast you can do it. And that's where the idea of power comes in. Power is just the rate at which you get work done. If you have more power, you can make that same 650 joule deposit, but you can do it in a lot less time.
And this comparison makes it super clear. Imagine a person and the forklift both do 500 joules of work to lift a crate. The work done is exactly the same. But it might take the person a full 10 seconds of straining. The forklift, it does it in 1 second flat. Because it did the same work in less time, we say the forklift is 10 times more powerful. So it's something to think about, right? The next time you're moving furniture, you're in a battle between your push and friction. The network determines if it moves. But the real question might be, how much power can you generate to get the job done before you run out of pizza? That's the physics of work and energy right there in your living room.